Hey guys, in this video we'll be solving yet another exercise on energy conservation. However, this time it will be quite more involved, and if you want to start with a basic exercise, then feel free to check out the first video on energy conservation, where we go through the basic concepts and solve a very simple exercise. The link, of course, can be found in the description below. Also, as always, if you have any questions along the way, feel free to ask them in the comments down below. At this point, I still respond to every comment I get. And with that said, let's get straight into it. In this specific exercise, we are going to look at the motion of a simple pendulum. And let me just draw a sketch of this pendulum such that we can more easily annotate it and at the same time define some quantities. We simply have a pendulum with a mass attached at the bottom, which can swing back and forward. The length of the pendulum we call capital L, and the mass at the end of it will be 10 kilograms. And the problem that we're going to solve now using conservation of energy is the following. Let's say that we pull this pendulum to its initial position, which would be a position where the angle with the straight line down is 45 degrees, and there we just suspend it. And naturally, if we would now let loose of the mass, it will swing down. And this brings us to the specific question that we will answer, which is what will be the velocity of this pendulum or of this mass when the pendulum crosses the line where it hangs straight down, so at this point right here. Now you could solve this problem using only Newtonian mechanics, but these calculations tend to become quite tedious, so let's instead solve this problem with the principle of conservation of energy. And this fundamental law of physics basically says that the total energy of a system remains constant throughout time. This means if we compare two situations of the same system, but at different times, then the total energy will be the same for both scenarios. And in these simple dynamical problems, we know that the total energy of the system will be equal to the kinetic energy, noted by a K, plus the potential energy. And again, to get more detail about this, you can visit the previous video on conservation of energy. So how can this now help us to solve this problem, namely to find the velocity at this specific point given our initial conditions? Well, it is by finding two scenarios of our system, two different points in time, for which we can compare the total energy and use its conservation so that it needs to be constant in order to provide the equations that we need to solve the problem. Now, it's important to realize that we can choose any two scenarios, for example, our initial condition and just one random second later. However, to take full advantage of the conservation of energy, we choose two specific scenarios. The first scenario, where the kinetic energy is equal to 0. Now, since the total energy is equal to the kinetic energy plus the potential energy, that would mean that the total energy for this scenario is simply equal to the potential energy. And then for the second scenario, we choose it the other way around, where the potential energy is equal to 0, which means that the total energy for this scenario will have to be equal to the kinetic energy. And then using conservation of energy between these two scenarios, we will get an equation that will help us to solve the problem. And finding these two scenarios is oftentimes the most tricky part. And that's what we will start with. And let's do that right now. Let's first look at scenario 1, where the kinetic energy with a superscript 1, because we're looking at scenario 1, is equal to 0. And consequently, the potential energy with superscript 1 is equal to the total energy of the system in this scenario, which we will later use to compare with the total energy of the other scenario. Now, since the kinetic energy is simply equal to 1/2 times the mass times v squared, the velocity squared, therefore we know that the kinetic energy is 0 only if the velocity of our object is 0. And this is of course the case for our initial position, where we are just lifting the weight and suspending it on the pendulum. And since it is not moving, its velocity is 0 and therefore its kinetic energy is 0. So this means that we need to find the potential energy of this initial position. We know that the potential energy is equal to its mass multiplied by the gravitational constant multiplied by an h, which is a distance. And in this scenario, it might not be initially clear what this h actually is. And therefore let's spend some more time finding this h. Normally, in very simple problems, this h is simply the height of the object above the ground. But that is quite arbitrary, because only differences in height actually matter. So it doesn't really matter where exactly you put the zero of our x-axis, as long as you're consistent within comparing different scenarios. For instance, we can define this h, which is the height of our object, compared to the lowest point that our object will get. Now in this case, with the pendulum, that is of course this point where the pendulum hangs straight downward. And conveniently, this is exactly the point at which we would want to find the velocity, which is our original question. And this already hints to what scenario 2 will be. So now that we have defined this h as the height above the lowest point that our object will get, we still would want to rewrite it as a function of the properties of our system as defined in our exercise. For example, the length of the pendulum and the angle of our initial position. So how do we now indeed rewrite our h as a function of these features? We know that the entire distance from the ceiling to this lowest point is simply L, the length of the pendulum, since the object is at the lowest point when the pendulum hangs vertically and the pendulum has length L. This means that if we project our h onto this vertical axis, we can define this distance right here. And this new distance will then simply be L minus h, right? Because we have the full length of the pendulum minus this h right here, which will be this distance, of course. Having defined this distance L minus h, we see that we naturally find a triangle, namely if we extend all over the pendulum and then this projection right here, we see that we have a triangle. And let me just redraw it over here so we can do some trigonometry. We know that this angle is the angle alpha. We know that this length is L and this straight length is L minus h. Reminding ourselves that we need to find this h right here as a function of L and alpha. Now doing some trigonometry on this angle right here, we find that the cosine of this angle is equal to the length of this side right here, so L minus h, divided by the length of the other side, so divided by L. And we see that we now have an equation that involves h, the parameter that we're looking for to get our potential energy, and the other terms all contain parameters of our system, namely L, the length of our pendulum, and alpha, the angle of our initial position. So we can rearrange this equality sign so that we have h on one side. And this gives us that h is equal to L multiplied by the cosine of alpha, and this gives us that h is equal to L multiplied by 1 minus the cosine, and we find that h has to be equal to capital L multiplied by 1 minus the cosine of alpha. And we see that we have found an expression which links h, the height that we're looking for, with an expression that only contains properties of the system, the length and the initial angle. And now we can simply fill this expression that we found for h in our formula for potential energy. And therefore, we find that the potential energy of our first scenario, which is in this case equal to the total energy of our first scenario, is equal to m multiplied by g multiplied by capital L multiplied by 1 minus the cosine of the angle of our initial position. And even though we know that alpha is equal to 45 degrees, which was stated in our problem, let me just leave this alpha as a general angle right here, which makes our result more general. And then later we can fill it in to see if our result actually makes sense. So let's remember this formula for later, and let's go to scenario 2, which we will use to apply conservation of energy to. And the hardest part is already done because this scenario will be much easier. To remind ourselves, in the first scenario we had that the kinetic energy was 0, but in this scenario we're actually going to look for a case where the kinetic energy is simply 1/2 times m times v squared, so not 0 basically. However, we are looking for a scenario where the potential energy is 0, which means that our kinetic energy will be the total energy of this scenario. And all these superscripts are of course to indicate that we are dealing with scenario 2. So in what scenario will our potential energy, which is m times g times h, be 0? Well, obviously when h is equal to 0. So this distance right here should be 0. Now you see that we've conveniently set this up because this will of course be the case when our pendulum is hanging straight down. Now don't let this static picture confuse you. At this point, the pendulum still has quite a large velocity v in that direction when it swings towards the other side. And at this point, we're already basically done with this scenario because we found that the total energy of this scenario, scenario 2, is simply the kinetic energy, and this is equal to 1/2 times m times v squared. Now, just to remind yourself, this v is exactly what we're looking for. That was a question. What velocity does our pendulum have when it is hanging straight down? And now to actually solve this question and to take this problem home, we are going to use conservation of energy, which says that the total energy of the first scenario, which was simply our initial position, will be equal to the total energy of our second scenario, which we found right here. And since we've already calculated both these total energies in both scenarios, we can now simply put them equal to each other. And just as a reminder, for the first scenario, we had only potential energy. And for the second scenario, we only had kinetic energy. And thus we can readily fill them in. We had for the potential energy m times g times capital L multiplied by 1 minus the cosine of this angle alpha. Now for the kinetic energy in the second scenario, we simply had the general formula, namely 1/2 times m times v squared. And if we now take a closer look at this equality, we see that we're practically done, because we have v, the property that we're looking for, on one side, and all of the other terms we actually know. We know alpha, which is 45 degrees. We know L, which is just the length of the pendulum. We know m, which is the mass of the pendulum. And we know g, which is the gravitational constant. So we can simply rewrite this equality sign such that v is on one hand and all of the other terms are on the other hand. But before we do so, we see that m appears on both sides of the equality sign. Therefore, we can simply cancel m out. So let us now do some simple algebraic manipulations to indeed rearrange this equality sign. First, we can put this 1/2 over here to the other side of the equality sign to get a 2. So we have 2 times g times L multiplied by 1 minus the cosine of our angle alpha, which is equal to v squared. And at this point, we can very easily take the square root on both sides of this equality sign. So we get on the left-hand side the square root of 2 times g times L multiplied by 1 minus the cosine of alpha, and we close the square root. And on the right-hand side, we simply have v. So at this point, we have found our solution. We have that the velocity when our pendulum is hanging vertically is simply this left-hand side right here. And at this point, we can do some checks to see whether our result actually makes sense. We see that this velocity will be larger when the gravitational constant is larger, and this makes perfect sense. When objects are pulled more strongly towards the Earth, they will fall at a faster rate, and therefore they will have a larger velocity. So basically, on Jupiter, a pendulum will go faster than it will on the Moon. Then we see that if the length of the pendulum increases, the velocity will also increase. This basically just says that we can pull the object at a much higher height above where it is at its minimum height if we have a longer pendulum. So this also makes quite a lot of sense. And then we have this term right here, which involves this angle alpha. And just to remind ourselves, this angle alpha is the angle of our initial position compared with the vertical line. Therefore, we see that if our alpha is equal to 0, so the initial position is just hanging straight down vertically, then we have, of course, that our cosine of alpha, which is the cosine of 0, is then equal to 1. And therefore, this term will become 1 minus 1. And so the square root of 0 will be 0, and our velocity will also be 0. And this makes perfect sense, because if our initial position is just hanging straight down, then, well, it will not gain any velocity. It will just hang there doing nothing forever and ever. If on the other hand, we will try to find the maximum alpha, where the cosine of alpha is equal to 0, we know, of course, that this will be the case when alpha is equal to 90 degrees. And this corresponds to the scenario where our initial position is simply the pendulum hanging horizontally. And because it hangs horizontally, we know that it will have the highest possible height above the point where it will hang vertically. And therefore, it makes perfect sense that in this case, we have our maximum velocity. And this brings us to the end of this video, and I hope that you are now more familiar with how to solve problems using conservation of energy. If you appreciate the time and effort that goes into making these videos, consider giving them a thumbs up. Of course, you can also subscribe to get notified by future releases. And with that, I thank you for watching, and I will see you in the next one. Bye.